Welcome to Module 17. We're going to take a look at right triangle trigonometry. So this is going to expand our view that we've been looking at the unit circle so far. It is very helpful if you have gone through the measuring triangles activity already, as it will give you a concrete understanding and feel of some special right triangles. But in here, we're going to be using right triangles to solve some application type problems. So first, a little bit of review from the unit circle. Okay, I've got my marker here. So you'll hopefully remember that when we started from the unit circle, we had, what made it a unit circle is it had a radius of one unit. In the measure triangles activity, it was 1 decimeter. Okay, so whatever, 1 unit. And then in that case, there is a, that radius will make a connection to the circle someplace, right? And that gives us an x and y coordinate. And as we studied before, those x and y coordinates also form a triangle. So we're seeing this connection between the unit circle and the triangle. And when we were using it in connection with the unit circle, we generally only talk about one of the angles, and that was the central angle here. We don't talk about this upper angle, although there is an angle up there, right? And in this lesson, we'll see how we can also include this upper angle, because we sort of get rid of the idea of a unit circle and we just look at the triangle itself. Okay, just remembering that x is cosine theta and y, the y coordinate, is the answer to the sine of whatever angle is down here, and we'll see how that works. We also have got the Pythagorean theorem here that is related because we've got a right triangle. So all these things are connected as we go through understanding these connections between the unit circle and right triangles. So let's go further. Instead of just looking at a hypotenuse of 1, we're going to allow the hypotenuse to be anything it needs to be. And so we've got these this triangle set up like this. We'll remember that, again, I say remember only if you've gone through the measure triangles activity, that these different sides of the triangle, we call it the hypotenuse, the opposite side because it's opposite the angle that we're considering, and the adjacent side because it's next to the angle we're considering. Now, if we consider the one at top, the two legs switch sides, right? So these are descriptive names. So it's only this side is the opposite only as long as we're talking about this angle, okay? So it's descriptive in reference to the angle. As soon as we come over, let me just change colors. If we wanted to talk about this angle, we'll call it something else, maybe beta, no, you're Greek, then this side, the side opposite, is now over here. And the adjacent side to the beta angle is over here. Okay, so that's one of the things to keep track of. These sides are not set in stone. So this side over here is not always the opposite side. It depends. It's always in reference to the angle we're talking about. And then once we have it set up, so if we're talking about theta, the red angle, so I'll go back to my, or is that orange? So the sine is now going to be considered the opposite over the hypotenuse. When we had the unit circle, the hypotenuse was 1, so this really isn't anything new, but it's more generalized. So the hypotenuse could be at any number. It could be 2, 3, 5.6. Okay, so we now think of the sine theta as a ratio of two sides, and cosine theta as the ratio of the adjacent over the hypotenuse. And that leaves us with the tangent as being the opposite over the adjacent. Another definition we use for tangent is that it's also considered sine. Remember, sine is kind of connected with the y value, and cosine, which is connected with the x, and tangent is the change in y over the change of x from algebra. But if we do these two, you'll see sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And what happens is when you take a fraction, you're dividing it, you flip it and multiply. Again, this is a little bit of a long explanation, but it helps to show you how in trigonometry we get, so we're going to change the bottom, we're going to invert it and multiply hypotenuse over adjacent, and then the hypotenuses cancel, and we have opposite over adjacent. But again, once we get going, we remember these, but it's also good to see where it all comes from. Okay, so these will be our trig functions. We'll actually be able to plug them into our calculator and come up with values. So this activity, what we'll be doing is what's called solving for triangles, or solving triangles. And what that means is every triangle has 6 characteristics that we're interested in. It's got 3 angles, and we'll label them with large letters. So A, B, C. So these are our angles. And C is always going to be the right angle, so that's a 90-degree. Sometimes we think, oh, they didn't give us enough information. But since we're always dealing with right angles, we always know one of them, and that'll be the large C angle, is 90 degrees. And then there's the lengths of each of the sides. And you see with a triangle, there's a relationship between the angle and the sides. The largest angle will always have the largest side. That's why the hypotenuse is always going to be the longest. Because if one of the angles is 90, the other 2 angles have to share 90 degrees. Remember, a triangle, the total of the 3 angles is 180 degrees. So once 90's been taken, that definitely says C will always be the longest side. A and B will be shorter than C. Now, and then B is the longer one, as you can kind of see here. It's got a larger angle. So there's all these relationships that we will use. But when we set up our problems, we'll kind of use labeling in this way. Now, when we go to use our calculator, we have to remember there are 2 modes. There is degrees and radians. And again, whatever version or brand you're using, you'll need to get comfortable with changing the mode. On a TI-84, there's this button here that says mode. So we're going to click on that. And this comes up and it shows us all the modes. And let's see, which one do we want? Okay, it's about that's 1, 2, 3 down, radian or degree. A lot of so we're currently in radian because it's highlighted, or it's shaded. So I'm going to go down. Most of the problems we're going to be working today are in degree. So I'm going to go over to degree and hit enter. We are now in degree mode. It's key because otherwise when I enter numbers, the calculator assumes those are radian numbers, not degree numbers. So something to remember, especially when you're taking a test, you may have problems that go back and forth between radian and degree. Remember to change your mode. And then I do second quit to kind of get back. Notice quit is in blue, so I hit the blue button that shifts it. Every key, or most every key, has 3 options. They have the blue option, like this one down here is the apps button. But if I do the second, that's going to give me the blue, which is angle. And the green, if I click on the green button, that would give me the letter B. So that's how we go through with each of these. Okay. So let's work a few examples. Oh, I'll have to fix this, but since we're in the mode, my example 1 got moved down. So we'll start with example 1 and then we'll work backwards to the other ones, and I'll get my PowerPoint or Google Slides fixed up. So first, we want to solve a triangle. What that means is we want to get the sides we don't know. We're given two things that we do know. Little a is equal to 5, and remember that is going to be draw a right triangle. And we start, usually this is going to be our big C, so this would be little c. We'll put our big A up here, which means little a's down here. And again, as long as you're consistent in your labeling, you'll be fine. So we know that A is going to be equal to 5, and then we're told that the angle B is 63 degrees. Round the lengths of the sides to 1 decimal place, and round the angle measures to a whole number. That's just what we're being told. So what we want is the things we don't know. So since we know, underline them here, we know B and we know little a. So the other things we're going to want to know is we want to know big A, big C, actually I'll go ahead and list them all here. We already know B, so we'll put that in there. 63, and then underneath little a, which we know is 5, little c, little b. Okay. Now, big C, we also know, I'm going to put this in red, we know that that's 90. They didn't give it to us directly, but because that's the right triangle. So then what we can do is we can find A, angle A, by simply adding these C and B together and subtracting it from 180. So 180 minus 90 plus 63. 90 plus 63 is 153. And so that's going to be 27. Okay, so if we're given one of the angles, that's always usually the easiest to find the other angle. Now we need to find C and B. So we can do that by using a trig function. So let's go ahead and maybe solve for C, because we know A, so we know the adjacent, we know the angle here, so we know the angle of 63, what's adjacent. If we back up quite a ways, here we go, something that has the adjacent and the hypotenuse will be cosine. Okay, so that's, we're kind of always using these. There we go. So we know the cosine of this angle, cosine of 63 degrees, needs to be equal to the adjacent side divided by the hypotenuse side, which is little c. So now we can just solve for C, and one way is using some algebra. So we will multiply both sides by C to get it up, and then we will divide both sides maybe at the same time, right? Divide both sides by cosine of 63 degrees. So just to emphasize, it's going to be in the denominator. So the C cancels out here. Cosines cancel out here. So we're left with that c equals 5 divided by the cosine of 63 degrees. And so then we come over to our calculator and we can just put that in. 5 divided by cosine. Notice how it gives us the parentheses. We already checked to know that we are in degree mode, which is important. Otherwise we won't get the right answer. And we get 11.01, and they want it to one decimal place, so we can just do that as 11.0. That would be one decimal place. And notice it's bigger than 5, so that's good. If we got a number that was smaller than 5, we'd say, wait, there's a problem there, right? So now we just have one last thing to find. We need to find this side. We need to find little b, and then we're done. Now little b, we could look at it as opposite over adjacent. And we could also use some of the other sides, but I'll tell you what, when you're solving a triangle, it's always best to use the information you were given. Because if we made an error in doing a calculation, then any calculations based on that, say using angle A, if I made a mistake here, it would just perpetuate that mistake. So if I use the ones that were given to me, I'm less likely to perpetuate a mistake. So I'll at least get B right because that was given. I'll get C right. So if I had A wrong, again, I could use it. I could use A and use B as the adjacent. But the way I'm going to do it is go with opposite, right? Opposite here over adjacent. So that's a tangent function. Okay, opposite over adjacent. So then I can say, well, the tangent of 63 degrees is opposite, which is B, over adjacent, which is 5. And you'll see that this calculation is actually quite nice. I just need to multiply both sides by 5. That cancels and that cancels, and B is just going to be 5 times the tangent of 63. And that we can plug in over here. 5. Oops. The tangent of 63. 9.8 because they want it rounded to one decimal place. So let's go ahead and do that. And we see from our drawing that sort of makes sense because B should be bigger than A because it's 63 degrees, A is 27. So we do a check for does everything fit? Yeah, hypotenuse is the biggest, then B is the next, 5. Okay, so it's all making, it seems to be good. All right, so now let's go back to 2, and we'll do, as you'll see, there's really only 2 more examples. Same thing, but this is now going to be applied to finding the height of a pole and casting a shadow. So a shadow we can just generally measure because it's on the ground. So a pole casts a shadow of 16.5 feet. We've got an angle of elevation. Now this is, so an angle of elevation means as you look up, right? Here's our little observer, sort of the angle between the ground and your view. So that's your angle of elevation. And then how tall is the pole? So what do we got going? We've got a pole. We've got the sun over here, casting a shadow. And as you see, that forms a triangle with the ground, a right angle here. So we're told that the shadow is 16.5 feet. We're told that the angle of elevation right here is 42 degrees. And now we just need to find everything else. So now on this one, we don't have to worry so much about solving the entire triangle, but all we really need to know is how tall is this pole. So let's see if we do our labeling, right? This should be big C, little c. We don't need to solve for how long the shadow is, or the top, but the important part is this. So we could call it either A or B, right? Maybe we'll call this B, we'll call this A. So that makes this angle B and this angle A. And so we don't really have to find angle A. All we need to do is, what is B? So B, if we look here, which is really nice, we don't have too many calculations. We have an angle. B is the opposite side, and we're given the adjacent. So opposite over adjacent would suggest to us that all we have to do is find the tangent of big angle B. Right, so this is going to be the opposite over the adjacent for this will be equal to the tangent of 42 degrees. And again, the algebra on this part is pretty straightforward. We just multiply both sides by 16.5. 16.5 divided by 16.5 is 1. So side B, the height of the pole, is going to be 16.5 times the tangent of 42 degrees. And so we just come to our calculator, enter that in. And again, we always want to make sure we're in the right mode. If you look at your calculator, where does it give us? Decimal, floating, degree. It's right there. So you can kind of look, okay, do a check. We don't actually have to go into mode. The Alex calculator does the same type of thing. It has some place where it'll say whether it's in degree or radian mode, because that's important. Got to make sure, double check. So it's 14.8566, round to the nearest whole number, so that's going to be about 15. So B would be equal to 15, rounded to one whole number, 15 feet. Okay, so using trig, we can actually, be able to take a tape measure, measure the shadow. Measuring up to the top of the bowl at 15 feet might be a challenge. We could do it maybe with a ladder, but this is the way we can use trig to get these things. So now we've got a ladder against the wall. We've got a 17-foot ladder leaning against a brick wall. The foot of the ladder is 6 feet from the wall. So let's say we've got a wall here, right? Got the ladder leaning against the wall. We know that the ladder itself is 17 feet. I don't know why I do that. I said 17. I was thinking 17, and for some reason I just wrote 14. A 17-foot ladder. We're also told that the foot of the ladder is 6 feet from the wall, so this Again, the wall we're assuming has a 90-degree angle, not the leaning tower. Find the angle the ladder makes with the wall. The angle the ladder makes with the wall. Okay, so here's the wall. It's got to be this angle here. Okay, so this is going to give us some experience with, changing things. Usually we're doing this like this one down here, right? So if we're doing this angle, let's see, this would be big C, little c. I guess we usually call this one up top big A. So this is little a. And then this would be big B, which we don't need to get, little b. So if we're looking at angle A, we know that the opposite over hypotenuse will be this one. So what the information we're given is opposite, and we're given the hypotenuse. Opposite over hypotenuse is going to be sine. That will give us our sine of our angle. So the opposite is 6 over 17 is equal to the sine of A. So we can plug that in. One way to get to the angle when we know this ratio is we know the sine is going to be 16. So let's kind of put that in there. 6 divided by 17. So 0.3529. And what we've got is with sine, there's something called an inverse sine. So what the inverse sine does is if you take the ratio of the sides, it will give you actually the angle. So the way we can go about this is using our calculator. We're going to plug in the inverse sine. Now we have a unit we'll do a little bit later that we actually talk about inverse functions. But what's really happening when you take the inverse, I guess there should be a parentheses here, is that an inverse and its function sort of cancel each other out. We did this back in algebra. So what we're going to get is that angle A will be equal to this calculation. To get the inverse sine, we do a second sine. Notice it's sine inverse. We could just do 6 divided by 17. Rather than plugging in the decimal equivalent, this will give us as accurate as we need to be, and to the nearest degree, so that's 21, right? Because a 6 gets the 2 to go up, so we would round that to 21 degrees. That's the angle it's making with the wall. And again, maybe we do this because maybe for safety reasons there's a minimum angle or something, or max, the safety angle. So this will allow us by, we know the length of the ladder, how far out we can come. So those are the types of problems you'll be facing in Module 17. And now we come to the end. We've done our direct instruction. What you need to do now is complete the learning activities. Remember, we have online tutoring. We have our instructor office hours. Contact me, and we can work things out. And also working with peers through the various discussion forums. So good luck, and thank you for listening.